So all of the series work that we have done up till this point, we've primarily been considering series that where all the terms of the series were positive. And then when we were looking at that series, we would try to figure out whether the total we got from adding up all of those numbers converged to a value or diverged. So let's do a little bit of refresher work and put some series in our mind so that I can then introduce the idea of an alternating series. So remember or consider the series as k goes from 1 to infinity of 1 over k squared which is 1 plus 1/4 plus 1/9 plus 1/16, etc. So every time we're looking at a series, our goal now is to imagine whether we think it converges or diverges. So anybody want to speak up with an opinion about whether this converges or diverges? Wenzel thinks this converges. Anybody else have an opinion? Either on chat or just chiming in by unmuting your mic to answer up. Any feelings? Another converge in chat. Okay, so a few people are saying they believe it converges. Could we justify that or say why we think that converges? P-series test was offered up, that's correct. So the P-series test says when you have a power function like this, 1 over k raised to some power p, in this case p is a 2, that the series will converge if the p-value is bigger than 1, and it will diverge if the p-value is less than or equal to 1. So yes, this converges. Converge. Now, let's also consider the series as k goes from 1 to infinity of 1 over k. So this is like the one above it, but I just don't square the k value on the bottom. So this would be 1 plus 1/2 plus 1/3 plus 1/4, etc. And whenever you're looking at a series, we're wondering, do these numbers add up to a finite total or something different? So opinions on this one?
My screen froze. It's the 1 over k series.
Yes.
So the harmonic series?
Correct. So one of the ways to help is to identify it as the harmonic series. And do we know that converges or diverges?
Yeah, it diverges.
Nice. Very good. Wenzel agrees. So this diverges. Okay, so here we have a couple of series in which we looked at them, we think about what they are, we think about what it means to determine whether they converge or whether they diverge. So the justification for the first one was the P-series test. The justification for the second one, the book explored that numerically, graphically. Then when I introduced the harmonic series, yes, exactly, it's a harmonic series. When we introduced that, I also talked analytically about how you could see that you're basically adding more than halves as many times as you want. But that actually now we could use the P-series test for this too, because when we introduced it, we didn't have the P-series test yet, but there was a theorem. And the theorem specifically stated, crazy. That is Jake or Jack or somebody who needs to be muted. Okay, there we go. Anyway, so yeah, we even had a theorem that specifically stated that this harmonic series diverges, even though now we could also establish that with the p-test as well. Okay. So basically what all these things have in common, and what a lot of the theorems like the ratio test and all of these different test theorems stated, was that the terms were always positive. These were always positive terms. So what's going to go on if you have a sum that's positive? When you're doing a series of terms that are always positive, then every time you add the next term in the partial summation, you're always adding more. So that means that the partial sums produce a sequence that is monotonically increasing, that you're always getting more and more and more and more. So if that diverges, the way it will diverge is because it's unbound, meaning that it goes off to infinity. So series with positive terms only, the only way they diverge is by going to infinity. And so therefore they either add up and just keep going and going and going and head off toward infinity, or they converge to a number like 0.9, 0.99, 0.999, 0.999, and they settle in on a value that way. So when we're thinking about convergence or divergence with only positive terms in the series, we're thinking about basically does the total sum settle on a value, or does it head off toward infinity? And that's the only way it can diverge. So now we want to consider an alternating series. An alternating series is going to be a series like the ones we've been looking at, but the only difference is that the terms alternate in sign. A positive, negative, positive, negative, positive, negative. And if that's the case, then it's a little bit more complicated in the sense that it's not going to keep increasing. You could have a series that diverges even though where the series diverges, but not because it goes to infinity. And we've looked at these before, like if the partial sums were like 1, 0, 1, 0, 1, 0, and kept going back and forth, well, then that diverges without going to infinity. So we're going to be considering now the idea of series where the terms alternate in sign. So an alternating, don't want to use red here, an alternating series, and let me give some page references. So, of course, it might be that you have a series where some of the values are negative, but they're not exactly alternating every time. It's like the minus sign is not on, off, on, off, on, off. But we're going to start by considering series where that's the case, because that's actually still pretty common. So when we have an alternating series, we're going to write it with a summation, because it's still a series, where k goes from 1 to infinity. But the way we're going to show that it alternates is we're going to put a -1 raised to a power as part of the series. And we're going to automatically make it where the first term is always positive. And the way we do that is making the power on the -1 be k plus 1. That way, when k is a 1, you have -1 squared, which is just 1. And when k is a 2, you have -1 to the third, which is a -1. And then after that, we're still going to have some a sub k, where the a sub k's are positive. So an alternating series is going to have basically, if you think about it, a sub 1 minus a sub 2 plus a sub 3 minus a sub 4, etc., where the a's themselves are guaranteed to be just positive numbers. And then the way we make the values of the series alternate is by writing this -1 power out front. And we're just doing that so that we can consider what the terms would be regardless of the sign, and then have the sign alternate as a separate way of writing it in the notation. So this gives us an alternating series. All right, so let's consider an example. So I'm going to take the series that we had above, the harmonic series, and see what it would be like if we caused the signs to alternate. So consider the alternating harmonic series. Which would be the summation as k goes from 1 to infinity of -1 raised to the k plus 1 times 1 over k. So 1 over k by itself is the harmonic series, and if I put this -1 with a power out front, then when I plug in a 1, I get 1. When I plug in a 2, I get -1/2. When I plug in a 3, I get 1/3, then -1/4, etc. So this is an example of an alternating series. And in this particular example, we're looking at the alternating version of the harmonic. Is that a question? Is that a question? Nassim, did you have a question or just no, just some unfiltered noise maybe?
Oh, no, I was just talking with somebody else. Sorry.
Okay. Yeah, no problem, no problem. We're all figuring out how to do this smoothly. It's hard to juggle all these things. Okay, yeah, but at any point, I don't mind if someone just unmutes their mic so that they can interrupt and ask a question. And of course, if you don't have a mic, I'm going to try to regularly look up at the chat box and spot if you have a question, if you want to type it in. But the easiest way would be so that everybody can hear it at the same time is if someone unmutes their mic, they just chime in with a question. I'm totally fine with that, okay? Okay, so that's what we have here. So this is our first example of an alternating series, and we're trying to get used to the notation of how we know it's an alternating series because you have this -1 with a power stuck in front of what we would normally write for a series. And then once we have this idea that we can consider notationally series where the signs alternate and there's these negatives, then we have to go back to the question that we always have for these things, which is, does the series converge or diverge? So because I chose to consider the alternating version of the harmonic series, we can think about the harmonic series itself. Does the harmonic series converge or diverge again? It diverges. We just were looking at that. That's right. So this is an example of a series where if it were not alternating, we would know that it diverged. But what happens when we make it alternating? Does that change things? So the first way to think about this is that, as I said before, if you're always adding positive terms, then the way you diverge is by eventually heading off toward infinity. But if we are changing the sign of the terms as we add them, then you're not necessarily always increasing. In fact, you're alternating between increasing and decreasing. So you might then say, is it possible that my series can avoid diverging when the signs are different than when they were all positive? Is the fact that I'm now adding that some of my terms have minuses on them, does that change whether it goes to infinity or not? And so this is the example we're going to use to explore that. So the first thing to think about is that, well, if I add up all the terms, I head off toward positive infinity. The very fact that some of them have negatives in front of them mean that there's potentially a lower value. That as I do the partial sums, that I don't get something that heads off to infinity, because now instead of adding all the time, now sometimes I'm subtracting. So the fact that some of the values are subtracted instead of added should give me less of a grand total than I would have had before. Now, if they're both going off to infinity, then so be it. But it might be that instead we don't go to infinity. That maybe somehow it diverges in some other way, like oscillating or something like that. So this is the thing we want to explore. So we can try to explore in this series kind of the way we did before. We could do it analytically. the book explores the alternating harmonic series on page 650. So let me put that in. This is on page 650. And they explore it numerically as well as graphically. Oops, that's what I meant to do. That's what I meant to do. There we go. So I'm going to have us consider this a couple of ways analytically, and then see if we can then, if that supports the conclusion that the book shows us. So let's consider, if I thought about, well, normally I would look at the partial sums. Let's consider the partial sums for the even values of the partial sum. Like, let's say we added up the first two terms only. The first two terms add up to a 1 minus a half adds up to a half. Then let's say I went further down in the partial sum. Instead of going the first two terms, I went to the first four terms. So then I'm going to get the 1/2 I had in the beginning, plus I would need to add up the next couple of terms as well. And again, you can add these in any order. So if I add first the 1/3 and the -1/4, and then add that to the 1/2 I started with, 1/3 minus 1/4 is 1/12. So I'm going to have 1/2, and then I'm going to add to that 1/12. And now if I generalize what's going to go on in the future here, the next term after the -1/4 would be a positive 1/5. And then I would be adding to that a negative 1/6. And that each time I go two more terms down the line, I get a total that is positive, because I have a number that was positive added to a number that was negative that was smaller. Every time I go down in the sequence, 1/4, 1/5, 1/6, 1/7, 1/8, the size of the next number is smaller than the preceding number. And so if my next two numbers that I'm joining in on my summation were a positive and a negative number added together in that order, then the positive one would be larger than the negative one was, and the total sum of those together would be positive. So basically, if I'm adding the partial sums down the line, I can recognize that the total for this series, if it converged somewhere, would have to be some number that could be expressed as 1/2 plus an infinite sum of positive values. And this, as a sequence of partial sums, is bigger than 1/2 because I keep adding to that. And the result would be a monotonically increasing sequence that led to a total. 1/2 plus a positive, plus a positive, plus a positive. So 1/2, a little more, a little more, a little more, a little more. So I know that the total for my series has to be larger than 1/2. It's bound below by 1/2. And I know that it's something bigger than that because the partial sums for the even partial sums just keep going up and up and up and up and up. So what do I get from this? That the series total the series total is more than 1/2, and it's monotonically increasing after that, using vocabulary from before. But it could still diverge because I have 1/2 and then I'm adding and adding and adding. Maybe it goes off to infinity. I know it doesn't go up and go back down after 1/2 when looking at pairs of values, that it's monotonically increasing when I consider pairs of values. So I know it can't go below 1/2 or something like that. But all right, so then Now we're going to consider this another way, analytically. So I can do the same thing by looking at odd terms of the partial sums. If I look at the odd terms of the partial sums, I start with a 1. That's S sub 1. But then if I go up to S sub 3, I would add the next two terms together. So if I do that, I have negative 1/2 plus positive 1/3. And the common denominator is 6 there, so I have negative 1/6. Then if I went up to S sub 5, maybe I'll put in a 1/5 here. Then when I add the next two terms together, I would have negative 1/4 and positive 1/5, which is negative 1/20. And so when I'm looking at the total this way, what I can see is that the sequence of odd partial sums begins with a value of 1, but then any time after that, as I go further down in the sequence, I'm going to add a decreasing in size negative number. Because for each of the pairs that I add to go from the 3rd to the 5th to the 7th to the 9th partial sum total, I'm going to have a pair of numbers where the first one was negative, and then we added a positive. But that the negative number was first, so it was larger in size. So when I add a larger size negative number to a smaller size positive number, I always get a negative result. So I can then view that the series total is less than 1. And that when I consider the odd partial sums, I have a monotonically decreasing value. So either way you think about this, the result of this series cannot go to a positive or negative infinity because it's bound above by a 1. You can see it as being 1 minus a bunch of little numbers that are getting smaller. And it's bound below by 1/2. You can see it as 1/2 plus a bunch of little positive numbers. And that each one of the even or odd parts of the partial summation of the partial series is a monotonic increasing or decreasing sequence that is bound. And if it's a bound and monotonic, it must converge. We have a theorem from previously that a monotonic sequence that's bound must converge. So that means this must converge. So therefore, the alternating harmonic series converges. So this was an analytical argument. And again, they also explore this numerically and graphically, and they draw the same conclusion. So our first example of an alternating series, the alternating harmonic series, can be shown analytically, numerically, algebraically, numerically and graphically, not algebraically at this point, that it converges. Questions, comments, discussions about that? Okay, so I'm trying to have us begin to wrap our minds around this concept. And so our first example was the alternating harmonic series, but let's look at this a little bit more broadly. the regular harmonic series, as we were just discussing, diverges. But when we cause the terms of the harmonic series to alternate in sign, then it goes from diverging to converging. So by taking the harmonic series and putting minus signs on every other term, it went from being a series where the total went off to infinity to being a series where the total converged. And if you look at their numerical and graphical analysis in the book, you can see that it converges to a number somewhere around like 0.7, approximately. It converges to a number less than 1. We know it's between 0.5 and 1 because we saw that it was bounded there in our analysis, but it looks more like something around 0.7 as a super rough approximation. It's just a number. It settles in on a value. It converges to a value. So the thing to recognize is that when you take a series and all the terms were positive, then the only way it can diverge is if that total of adding all of those up heads off toward infinity. And when you take a series like that and you then put in some minus signs on some of the terms, maybe half of them if it alternates, maybe not. But just by taking it and making some of the terms have negative sign will produce less of a total. And therefore, it may not go to infinity anymore. And the harmonic series is a quintessential example of that. The harmonic series, if you add up all the terms, they head off toward infinity as a total. But if you let the terms alternate in sign, then instead of heading to infinity, the total you get converges to a number that's less than 1. Questions, comments, discussions about that? Okay, so then this puts us in a position where we want to now think about considering alternating series separately, because this is a new world. And most of the tests that we did before applied to only series with positive terms, whereas now we can have a series with positive and negative terms. And that means, for example, we can't use the ratio test. We can't use the root test. All of those tests apply to terms with a series where the terms were all positive. So I will point out that the divergence test doesn't care whether the terms are positive or not, but we need a new test. So I'm going to clear this page. So now we're going to consider a test for the alternating type of series. So on page 650 still, we have Theorem 818. And this is the alternating series test. So we had a ratio test, we had a root test, we had a comparison test, we had a divergence test. Now we have an alternating series test. So the alternating series test is specifically for an alternating series. And it states as follows, that the alternating series that is written by a summation of -1 to the k plus 1 times some terms a sub k. And again, we're going to say that this is alternating because the a sub k's are understood to be positive numbers, and the only reason the series alternates is that each one of those is multiplied by a 1 or a -1 depending on the power of k you're looking at. So the alternating series, written this way, converges. Oops. Provided that two things are true. One, so the alternating series will converge if, one, the terms are non-decreasing in magnitude. i.e., or what does that mean? That A sub k is non-increasing, or non-decreasing. Non-increasing. So I screwed up both places. Non-increasing. So what that means is that the terms are not growing larger in size. They may stay the same for a while, but when they change in size, magnitude, meaning absolute value, they do not increase. They decrease instead when they change. So if, for example, the terms were getting bigger in size, like my terms were 1 minus 2 plus 3 minus 4 plus 5, meaning they're getting bigger and bigger even though they're alternating, well, then there's no way that series is going to settle in on a value and converge, because the amount that it's changing as you move down the line is increasing. And that's not going to work. You're never going to settle in on a value if the amount that you're changing every time you add a new number is getting bigger in any way. It needs to be getting smaller and smaller. That's a requirement. Now, let's say that's the case. So the alternating harmonic series was an example where those are getting smaller and smaller. But even more specifically, not only do they need to be non-increasing, the other condition they have to meet is that they have to be going to 0. So that the limit as k tends to infinity of a sub k is equal to 0. So how could they be non-increasing and not head to 0? So an example would be 1.1, 1.01, 1.001, 1.0001, things like that. That's a strictly decreasing sequence of numbers, but they're not heading to 0, they're heading to 1. So we need the terms to be getting smaller in size and actually heading towards 0 instead of heading downward towards some non-zero number. So if you have an alternating series that meets these two conditions, then it converges. So the alternating series test basically gives you a way that you can try to see if it converges. You need to have the magnitude be non-increasing every time. It's not allowed to increase at all. And you need to have the place that the values are heading toward it be 0. If that's the case, then it must converge. So there's 3 things that have to be met. These 2 conditions have to be true, and you also have to be working with an alternating series. So for example, let's look at our quintessential example we started with, the harmonic series by itself. The harmonic series, not alternating, but just the regular harmonic series, it meets conditions 1 and 2 here. The terms are non-increasing and they head to 0. The limit of 1 over k as k goes to infinity is 0. But it diverges. So why does it show that this test is wrong? Because it's not an alternating series. So if you add the condition that the terms alternate in sign, then after that, if you meet conditions 1 and 2 here, then you guarantee convergence. And notice that you need all 3 of these to be in place for that to be true, for this to hold. Questions, comments, discussions about this? Let me add one other thing to consider here. Looking at this second condition, the second condition is that the limits of the terms is 0, of the terms themselves in the series. So note if the limit as k goes to infinity of a sub k's is not equal to 0, then the series diverges by the divergence test. Okay, so you're expecting the terms will go to 0. And if you see that even though it's alternating, the terms don't go to 0, well, then you can say, oh, well, the divergence test says that this diverges right away. But let's say they go to 0, like in the harmonic series that's alternating. If the terms go to 0 and the series is alternating, then the only other thing is to say that they're strictly non-increasing. And if you can say that, then by the alternating series test, you know it converges. Okay, so let's look at an example here of applying this test. So take note, the divergence test applies to series whether they converge or diverge. I'm sorry, whether they're alternating or not. But most of our other tests don't. Like you're not going to be able to use the integral test because you're not going to have a continuous function if it's alternating back and forth. You are not going to be able to use the ratio test and all of those as well. They all specified that the terms have to be all non-negative. So you're not going to have them be alternating. So really, once you use the divergence test, we're kind of saying, all right, well, if it's an alternating series, I need to start with the alternating series test. So let's look at, oh, that was on page 650. Did I put that up there? Doesn't matter, I guess. Yeah, I did. I'm also going to mention real quick that like with the harmonic series, they went ahead and gave a theorem specifically to state that the alternate harmonic series diverges. So theorem 819 on page 651. The alternating harmonic series diverges. We just looked at that analytically. They look at it graphically and numerically. And using this alternating theorem test, you could show that the alternating harmonic series meets the criteria for the alternating series test, and therefore, I'm sorry, I said diverges, but I meant converges. Converges. So we have one theorem given earlier that the normal harmonic series diverges, and now we have a theorem that the alternating harmonic series converges. Okay, so the example one is on page 652. And let's say we take a look at A, and maybe we'll look at B too. Let's try A. Maybe I'll do A for you and then give you guys a chance to try B. So in A, we have a series as k goes from 1 to infinity. And it has a -1 raised to the power of k plus 1. So that's what's going to make it alternate. But then that is all over k squared. So what does this look like? Again, just to try to visualize what these things are as we get more abstract. If k is a 1, then I have -1 squared in the top, which is 1, and I'm dividing by 1 squared. So the first term is a 1. If k is a 2, then I have a -1 to the third power in the top, which is a -1, making this negative. And on the bottom, I have 2 squared, which is 4. So this would be plus 1/9 minus 1/16, etc. So as with any new series, we have our question, C or D. myself. So we might want to say, oh, well, it looks kind of like the P series with a 2 on there. So maybe that would mean that it converges, but this isn't a P series. The P series test applies only to positive term series. This is an alternating series, so we can't use the P series. But again, I'm going to keep pushing for this. We could try to form an opinion and then try to justify that. So it looks like a couple people are suggesting that it diverges. I do see somebody saying the limit of the a sub k's is 0. So that's true. If the limit of the terms was not 0, we could immediately conclude it diverged. But the fact that the limit of the terms is 0 gets us a step closer to convergence. We still need this part though. We need number 1. We need this one. The terms are non-increasing in magnitude. Is that the case? So magnitude, again, for those who just aren't used to that word mathematically, magnitude means absolute value. So then this means we're really sort of asking for number 1 from above is the absolute value of a sub k plus 1 less than or equal to the absolute value of a sub k. That's what that means. And in this case, when we take the absolute value, it just knocks off the possibility of the negative part on the top of the fraction. And we're just left with 1 over k squared. So the question is 1 over k plus 1 squared less than or equal to 1 over k squared for all k? So do we think that 1 over k squared is less than or equal to 1 over k squared? I'm sorry, 1 over k plus 1 squared is less than or equal to 1 over k squared? Yeah, exactly. Because if you make k a bigger number when you square it, then k plus 1 squared is bigger than k squared. But since it's in the bottom of the fraction, then that makes the denominator larger, causing the fraction of this to be smaller. So this part we would say yes. So therefore 1 is satisfied, and we already had someone point out that the limit as k goes to infinity of a sub k, which is 1 over k squared, is equal to 0. So that means 2 is satisfied. This is an alternating series. So therefore, by the alternating series test, that's an S, okay. The series converges. How do you guys feel about that? Or are there questions, comments, or discussion about that? Okay, so let me ask you to think about something here, because I've already asked you to think about it before, and we're going to need it in about 10 minutes. So what did we do here? We took the series 1 over k squared, and we considered the alternating version of that series by putting the little -1 to a power on it. And back originally, when I reminded us of these series, I put up 2 examples. I put up 1 over k squared, and I put up 1 over k. And we reminded ourselves that 1 over k squared converges by the p-series test, and 1 over k diverges because it's the harmonic series. Now we have considered the alternating version of both of those, and we found with the alternating version of the harmonic series that by alternating the signs, you took a harmonic series which diverged and turned it into an alternating harmonic series which converges. So adding the minus signs could take something that originally diverged and all of a sudden make it converge. So it's easier to converge when you're an alternating series. Then we took 1 over k squared and made that alternating. Well, 1 over k squared already converged. And then we see when we add some minus signs every other term, it still converges. And so I'm going to have you think about this idea. Adding the minus signs compared to having all of the terms be positive will increase the likelihood that it converges. It will never turn a series from convergent into divergent because you just have less. By having some of the terms negative, you have less of a total than you would have if they were all positive. And if when they were all positive, they already converged, then making some of them negative and getting less, you're still going to get convergence. That's going to be a theorem we have in a couple of pages. So, but that's something we can start to see here. So let's do this. This was an application of the convergence test. How to find what number series converges to is a question from Mohammed. Yeah, so basically the way I described that before was that we're going to have lots of problems where all we're doing is we're figuring out, does it converge or does it diverge? And we're not going to worry about what value it converges or diverges to, because that's hard to determine in most cases. What cases can we do it, and is it easy to do? Geometric series. No, it's not Calc 3. It's just not practical to try to do it algebraically or analytically. Instead, it's done numerically, that you just put in a big value of k and you let some fancy thing calculate it. We do have a couple of places where they talk about how you could begin to do that analytically. And again, it ends up by focusing on if you went up to a certain part, like if you went out 1,000 terms, there's still some extra after that, but they're getting so small that you can ignore that part because it's after a certain point in the decimal. And I've been suggesting that we not worry about that. So in a previous section, we had something where we looked at the remainder of a series. And in this section, we're going to do this one more time. They're going to give you a formula for an integral where you could approximate the remainder of an alternating series. And they don't spend much time on it. You can theoretically do it at this point, but the reality is that in modern days with nice computers, there's just no reason to go into the analytical side of that very far. Once we know that it converges and that it's not going to oscillate or diverge, then we can get our approximation with numerically with calculators whenever we want. So yeah, so for now, keep in mind that our series work, unless you have a geometric series, all of our series work after pretty much 8.3, when we're doing all these tests, we were no longer determining to what value a series converged. We only determined whether it converged or diverged, and we're going to leave ourselves satisfied with that for now. Okay, so now let me give you the next example problem and have you try to think about if you could figure that out yourself. Just to imagine being in the situation of looking at a series that alternates and trying to figure out whether it converges or diverges. So we just did 1A, so let's try 1B on the same page. And I'm going to write it up there, and then I'm going to shut up for a couple of minutes and let you guys think about it. So here's the series. Again, the instructions are the same. Determine whether the following series converge or diverge. Doesn't ask for the value, just C or D. So here it is. So this is still on page 652. This is example 1B. So the series is shown to you by just showing you the first 4 terms. It's 2 minus 3 halves plus 4 thirds minus 5 fourths plus, and then etc. And again, your goal is converge or diverge. So I'm gonna go refill my water. So I will be right back as you guys think about this for a minute. Yeah, good idea, Jack, change your mind. Yeah, so the thing to recognize about these is that the terms themselves do not go to zero. Now, how would you see that? Well, you could maybe get a sense of the fact that this, and again, we're talking about magnitude, not worrying about the plus or the minus, is that, that the numerator is always one more than the denominator. 5 over 4, 4 over 3, 3 over 2, and the first one even can be seen as being 2 over 1. So this is a sub k. So this would be a good exercise to think, if you could write this yourself, that this is the series of -1 to the k plus 1 of k plus 1 over k. And that if you take the limit, oops, not yet. And if we take the limit as k goes to infinity of a sub k, well, let's say we did the absolute value of these, then that would be the limit as k goes to infinity of k plus 1 over k, which is 1. And what does that mean? That means that as you go it off to infinity, these numbers are basically alternating between a 1 and a -1. So therefore, it diverges. It diverges actually by the divergence test. Questions, comments, or discussions about the alternating series test? Okay, so I was just alluding to this next part and why we're going to skip it. So right after that, they spend 1 page on the remainder in an alternating series. And it's a little simpler than it was in the previous one, but nonetheless, instead, rather we get to the absolute convergence implication and the definitions of absolute and regular convergence to finish off the section, as opposed to looking at the remainder. And if a problem shows up where they ask you about the remainder of an alternating series, then just take note that that's theorem 820. So note, and then just use that directly to do any problem that comes up. And if you have a question about it, you can ask me in office hours. So, but note theorem 820 on page 652. I'm going to leave for students to look at themselves. And it talks about the remainder or in or of an alternating series. So consult as problems require. Okay, so yeah, we have a couple of definitions to introduce, and then one more theorem and some examples to try to do to finish the section. We have about 1 hour and 10 minutes. So let's see if we can get those done. Then we'll take a little break. And then when we come back from the break, maybe we'll see if there's time to do a couple problems just from the exercises at the end of chapter 8. And I might even see if there's time to give like a 10 or 15 minute introduction into chapter 9. But we're not going to have anything from chapter 9 like for a couple of weeks. But there's a big concept in chapter 9, which is really hard for students often to wrap their mind around right at the start. And so I would like a little chance to introduce that so that students who are going to try to get ahead in chapter 9 have at least had me explain this idea of this big concept. So let's see if we can get to that. So, but let me clear the page here. Okay, so then let's look at this definitions. And they're right on what we've been talking about. So on page 654, we have definitions. So let me just write it out, and then we'll interpret and try to understand what it says. If a series of absolute values of a sub k's converges then the series of the a sub k's, where we don't make them all positive, converges absolutely. Yeah, that's how they phrase it. And if, whoa. Why is it doing that? Okay. There's some setting where it'll just start writing, even if I'm not touching the screen sometimes. I haven't figured this out. I apologize. That's better. A little bit. Whereas, if instead the absolute value series diverges, sorry, this has gotten all spotty, and the series, when they're not all positive terms, converges, then we say that the series of the a sub k's converges conditionally. So our definitions are converges absolutely and converges conditionally. And we've already had examples of both of these that we can refer to try to understand this idea. So basically imagine that you have an original series of all positive terms like 1 over k squared, where all the series of those positive terms of 1 over k squared converges. So actually maybe we can write that here. So that an example of the first case, the series of 1 over k squared. So that's a situation where, actually, I'll put a -1 here to the k plus 1. Okay. So let's say, example, series of -1 to the k plus 1 over k squared. So -1 to the k plus 1 over k squared is an alternating series, but it's one in which if I put absolute values on that and made the -1 go away and just had 1 over k squared, that would also converge. So that's a situation where the series of the absolute values converges, and then the series itself, when it's alternating, converges. So since that series converges, even if all the terms are positive, it still converges, then we say it converges absolutely. That by adding the negatives, we're not going to all of a sudden make it diverge, so it converges absolutely. However, if you had a series where when they're made all positive, it diverges, but if they are alternating, then they converge, we say that that series converges conditionally, because its ability to converge is conditional on the fact that you have to have the positives and the negatives. So the example of that, which is also what we did, is the alternating harmonic series. So if I have the -1 on the top with the k plus 1 divided by k, so this is a series where if the -1 weren't on the top and the bottom on the top alternating, if you just had 1 over k, well then your series would diverge because the harmonic series diverges. But when you add the alternating -1s, then all of a sudden you get convergence. So this alternating harmonic series is an example of a series that converges conditionally. So Wenzel's asking, does it go both ways? Which one are we talking about there? No problem. Okay, anyway, so these are examples. These are examples of the definitions of these words. So you use these words to talk about in more detail the convergence of an alternating series or a series that has any minus signs in it at all. And the big difference is you say, well, if we took away all the minus signs, if it still would converge, then we say the series converges absolutely. But if we took away all the minus signs and all of a sudden the series diverged, then we say the series converges conditionally. So when you're looking at an alternating series, there will be 3 possibilities. Possibility number 1, it simply diverges. Possibilities 2 and 3, it converges, and the distinction is, does it converge absolutely or conditionally?
Professor, when we're determining when it converges or diverges, that's when we would have to like do either like the divergence test or depending on like what test, right?
Yes, well, it could be we use the alternating series test like we just did, and you get that it converges. And we're going to have a theorem in a minute that would allow us to use some of our other tests as well. So I think you're asking about how do we figure it out if it converges, right, Prajit?
Right. Yeah, I was just wanted to make sure that I was like understanding how to figure that out. But that comes from the conditions that we mentioned earlier for like the alternating harmonic series. Like that one had, if the limit goes to 0, it'll converge, right?
Okay, so yes, you're a little bit ahead of the game because you're trying to sum up in your mind how do we figure out whether it converges. And right now, we don't really have all of our other tests because they don't apply to alternating series. We just have the alternating series test. So let me do this. Because you're trying to draw a conclusion that's a little bit ahead of where we're at without the next thing that we're going to do. Let me just write down the next thing that we're going to do, and then hopefully that'll answer your question a little bit more clearly. So on the very same page, just a couple inches below this definition is our final theorem for the chapter, I think. Yeah. So right below this, let's put theorem 821. And again, this is still on page 654. So it states the following. Absolute convergence implies convergence. So what is absolute convergence? That's where the series with the absolute values converges. Meaning if you didn't have the negatives on it, if it wasn't alternating, if it converges without alternating, that means that it converges. If it converges with all the terms being positive, then alternating them being positive and negative or putting any extra negatives in anywhere, it will still convergence. You will never convert a convergent series into a divergent series by adding some minus signs on some of the terms or even all the terms. That's what this states. So what this means is if you're looking at an alternating series, and as Parjit was asking about, if you're trying to answer the question, does it converge or not? Well, you can still use the ratio test and the integral test and all of those tests, but when you use those, you have to use it to the absolute value of the series. And if you take away the minuses and you make all the terms positive and you get a series that converges by any of those convergence tests, then it's absolutely convergent, and that means that the alternating version also converges, and you've got that it converges. The problem is that that doesn't cover all cases, because there are some alternating series, for example, that are conditionally convergent. So you might have it where you took the absolute value and you used the ratio test and you got that it diverged. But that doesn't mean that the alternating version also diverges. Does that make sense? Maybe not.
Yeah, no, I see that.
So basically, we can use all of our tests if we ignore the minus signs on an alternating series. And if any of them give you convergence, well, then you know the alternating version also converges. So that's what this theorem tells us.
Got it. So that's how we can determine it, by looking at what the absolute value of the by taking the absolute value, see what that gives us, either if it converges or diverges. So if it does diverge, that's when it's conditionally, so we don't exactly know.
Nope. No. Because conditionally converges still converges. And to say that it conditionally converges, the absolute value series has to diverge, but you also need the series itself to converge. And that you don't know yet.
Oh, right.
So what that means is if you get this part, if you take the series of the absolute values and you don't get convergence or you get divergence, that means you still don't know about the series itself, because the series itself could still diverge, or it could converge, which means that it converges conditionally.
Okay.
So that means if you can't get the absolute values to converge, it might make you suspect, well, that's maybe because it diverges. I don't really know. Well, then you still have two things. You have two choices. You could try to determine that it diverges because of the divergence test, because the divergence test doesn't care whether the terms are alternating or not. Or you can use the alternating series test to try to get convergence. And notice, part 2 of the alternating series test is to take the limit of the a sub k's and see if they go to 0. And that's the same limit you would do if you were trying to use the divergence test. So basically what's going on is if you use the absolute value and you get something that diverges or something, then that probably means that you need to take the limit of the terms themselves and make sure they go to 0. And if you take the limit of the terms and they don't go to 0, that means it diverges by the divergence test. If they do go to 0, then, and you have an alternating series, then all you need to know is show that the terms are non-decreasing in magnitude, and then the alternating series test gives you convergence. So that's a little complicated, but that's where it all fits together in the end. So let me write out what the theorem states with the proper language a little bit better. Basically, absolute convergence implies convergence can be written as follows. If the series of the absolute value of a sub k's converges, then the series of a sub k's converges. If you can get them to converge when they're all positive, then they're going to converge even if they're not. So we can use an example for this. Example 3 on page 655. Let's take a look at just A. Okay, so the instructions are determine whether the following series diverge, converge absolutely, or converge conditionally. So when you look at an alternating series like this, what this means is that our first instinct would be to ask ourselves, well, if I didn't have to worry about that pesky negative positive thing, do I think I could determine whether it converges or not? So in this case, consider the series of just 1 over the square root of k instead of an alternating 1 over the square root of k. Do we think that's C or D? Any opinions? Consider.
Then this to a k to the power of 1 over 2 is smaller than 1 according to the P series, isn't it? Diverge?
Correct. Very nice. Oh, I just circled the wrong one. You were right. I'm wrong. There we go. Yes, this diverges by the P series test. Because the 1/2 power is the same as the square root. So this is like 1 over k to the power of 1/2, and the power is less than 1. And by the P series, if you have 1 over k to a power that's equal to or less than 1, it diverges. So what do we just conclude then? We conclude that because the series of the absolute values diverges, that this is not absolutely convergent. But we still don't know whether the series itself converges or diverges. We do know that if it converges conditionally because the absolute value version diverges. But we cannot conclude that since the absolute values diverge, that the alternating version also diverges. We still don't know that. Does that make sense so far? Okay, so what do we have from this so far? We know that the series of absolute value of a sub k's diverges. So if we're not able to get that the series converges absolutely, then our only other alternative is to see if it converges or diverges using like the divergence test or the alternating series test. And in both of those, you want to consider the same thing. So I'm going to say now consider the limit as k goes to infinity of the magnitude of the terms in this case, or just the a sub k part, which is 1 over the square root of k. So if this is not 0, then the divergence test tells us that this alternating series diverges. But if it is 0, then we've satisfied part 2 of the alternating series test, and we'd have to look at part 1 to see if it does actually converge. So do we know the limit is k goes to infinity of 1 over square root of k? Chapter 2.
Zero.
Yep, a couple of people are saying 0. That's absolutely right. So that means that this fails the divergence test. The divergence test fails to tell us that this diverges. It doesn't mean that we know that it converges yet, but it also means that it satisfies number 2 of the alternating series test. So then part 2 for alternating series test is satisfied. Now going back to part 1, we have to say, is the a sub k, meaning ignoring the -1 part, non-increasing? Or is a sub k plus 1 less than or equal to a sub k for all k? So in this case, that means is 1 over the square root of k plus 1 less than or equal to 1 over the square root of k for all k? Opinions on that?
It looks like it's non-increasing. And for the second part of 1, the 1 over the square root of k plus 1. Oh, wait, I'm not sure about that.
In other words, as k gets bigger, do the values of the terms get smaller? Wenzel says yes. So think of it this way. If you add 1 to k, you get a larger number, and a square root of a bigger number is bigger, which means you have a bigger denominator on the left than you do on the right. And when the denominator is bigger in a fraction, and the top stays the same, you get a smaller number. So example, 1 over the square root of 7 is less than 1 over the square root of 6.
Right, that's where my brain was going. I got confused on the k plus 1 square root part.
3 steps in there, so it's certainly easy to get confused here. So basically, since as k gets bigger, the square root of k gets bigger, and that means that as the denominator gets bigger, the fraction gets smaller. So as k advances, these terms are getting smaller, and that means they're non-increasing. So that means that we say that part 2 is also a yes, satisfied. And it is an alternating series. So by the alternating series test, the series converges. And since the series of the absolute value of the terms diverges, we say the series itself converges conditionally. Which is what it asks. We're supposed to see if it diverges, converges absolutely, or converges conditionally. And in this case, with absolute values, it diverged, but without absolute values, it converged, and that's converging conditionally.